What if everything you see around you right now is not real? What if the screen you're looking at, the chair you're sitting on, the walls of your room, and even your own hands are nothing but an elaborate illusion? I know this sounds absolutely insane. I know this sounds like something straight out of a science fiction movie, but here is the terrifying part. Some of the greatest minds in physics, including Stephen Hawking, Leonard Susskind, and Nobel Prize winners, have spent decades seriously considering this possibility. They are not crazy people. They are not making wild guesses. They have mathematical equations. They have theoretical frameworks. And most disturbingly, they have evidence that suggests our entire three-dimensional universe might actually be a hologram projected from a distant two-dimensional surface. Before you click away thinking this is just another conspiracy theory, let me tell you something that will keep you watching. In 2017, a team of physicists published a study that found the first observational evidence supporting the holographic universe theory. They analyzed the cosmic microwave background radiation, the oldest light in the universe, and found patterns that match what we would expect if the universe were indeed a hologram. This is not speculation anymore. This is real science being done by real scientists at real universities. Let me give you some mind-bending facts before we dive deep into this rabbit hole. Fact number 1. According to the holographic principle, is all the information contained in your body, every memory you have ever made, every thought you have ever had, every cell in your body, could theoretically be encoded on a surface no bigger than a postage stamp. That is how efficiently information can be compressed in a holographic universe. Fact number 2. Black holes, the most mysterious objects in the entire cosmos, gave us the first clue that our universe might work like a hologram. When Stephen Hawking discovered that black holes emit radiation and slowly evaporate, he accidentally stumbled upon a paradox so profound that it took 30 years of intense debate among physicists to even begin resolving it. And the resolution? It points directly to a holographic universe. Fact number 3. Fact. There is a mathematical equation discovered in 1997 by a young physicist named Juan Maldacena that mathematically proves, that a universe with gravity in 5 dimensions is exactly equivalent to a universe without gravity in 4 dimensions. This is not philosophy. This is mathematics. And it is telling us something extraordinary about the nature of reality. Now I want you to really think about this. Right now, as you are watching this video, you believe you exist in a 3-dimensional world. You can move forward and backward, left and right, up and down. You can touch objects. You can feel textures. You can sense depth. Everything feels absolutely real and 3-dimensional. But what if all of this is an illusion? What if the true reality is a flat 2-dimensional surface somewhere at the edge of the universe, and everything you experience as 3-dimensional is just a projection from that surface, like a cosmic movie screen projecting the movie of existence, and you are both the audience and a character in that movie? If you're ready to have your entire understanding of reality shattered, then stay with me. By the end of this video, you will never look at the world the same way again. You will understand why some physicists believe we are living in a hologram, what evidence supports this theory, and what it means for your existence, your consciousness, and your place in the cosmos. But before we go any further, I need you to do something for me. If you believe that understanding the deepest secrets of the universe is important, hit that like button right now. It helps this video reach more curious minds like yours. And I want to know what you think. Before watching this entire video, comment below and tell me, do you think we live in a simulation or a hologram? I am genuinely curious to see what your intuition tells you. And of course, if you're not subscribed yet, subscribe now and turn on notifications, because this channel is dedicated to exploring the most mind-bending mysteries of space, time, and existence itself. Now, let us begin our journey into one of the strangest ideas in all of physics. But to understand why scientists think the universe might be a hologram, we first need to understand what a hologram actually is. And I promise you, holograms are far stranger and more fascinating than you probably realize. The story of holograms begins in 1947 with a Hungarian-British physicist named Dennis Gabor. Gabor was not trying to create 3-dimensional images. He was actually working on improving electron microscopes. But in the process, he stumbled upon something remarkable. He discovered that you could record not just the intensity of light, like a regular photograph does, but also the phase of light, which is essentially information about where the light waves are in their cycle of oscillation. This might sound technical, but the implications were extraordinary. By recording both intensity and phase, you could capture complete three-dimensional information about an object on a flat two-dimensional surface. Think about a regular photograph for a moment. When you take a photograph of a coffee cup, you get a flat image. If you move your head while looking at the photograph, you do not see different angles of the cup. The image stays the same because it only captured how the light looked from one specific angle. But a hologram is fundamentally different. A hologram captures light information from multiple angles simultaneously. When you look at a hologram and move your head, you actually see different perspectives of the object, just like you would if you were looking at the real three-dimensional object. The three-dimensional information is encoded in the interference patterns of light waves on the flat holographic film. Here is where it gets really interesting and directly relevant to our topic. If you take a hologram and cut it in half, something extraordinary happens. You do not get half of the image. Instead, each half contains the complete image, just from a slightly different angle and with slightly less resolution. Cut it into quarters, and each quarter still shows the complete object. This is a crucial property called non-locality. The information about the whole image is distributed throughout the entire hologram. Every piece contains information about the whole. Now I want you to hold on to this property because it becomes absolutely essential when we start talking about the universe. The idea that the whole can be contained in each part, that three-dimensional information can be perfectly encoded on a two-dimensional surface, and that this encoding is distributed non-locally. These properties are exactly what physicists discovered when they started investigating black holes and the fundamental nature of space-time. But we are getting ahead of ourselves. Let me explain how holograms actually work so you have a solid foundation. To create a hologram, you need a coherent light source, which means a laser. The laser beam is split into two paths. One beam goes directly to the photographic plate, and this is called the reference beam. The other beam bounces off the object you want to record and then hits the photographic plate, and this is called the object beam. When these two beams meet at the photographic plate, they create an interference pattern. You have probably seen interference patterns before, like when two sets of ripples meet in a pond and create complex patterns of peaks and troughs. The holographic interference pattern is incredibly complex, encoding all the three-dimensional information about how light bounced off the object from every angle. When you later shine a laser through the developed holographic plate, this interference pattern reconstructs the original light waves, and you see a three-dimensional image floating in space. It looks so real that your eyes cannot tell the difference between the holographic reconstruction and the actual object. Your brain receives the same light information it would receive from a real three-dimensional object. Now I need you to make a mental leap with me. For most of human history, we assumed that the reality we experience is the fundamental reality. We see three dimensions, so there must be three dimensions. We feel solid objects, so objects must be fundamentally solid. We experience time flowing forward, so time must fundamentally flow. But physics has repeatedly shown us that our intuitions about reality are wrong. Solid matter is mostly empty space. Time flows differently depending on how fast you are moving. Particles can exist in multiple places simultaneously until observed. What seems obviously true about reality is often an illusion created by our limited senses and evolved brains. So what if the three-dimensional nature of reality is also an illusion? What if the true reality is two-dimensional, and the three-dimensional world we experience is a projection, like a cosmic hologram? This might seem like pure speculation, but here is the remarkable thing. Physicists did not come up with this idea because they wanted reality to be weird. They were forced into this conclusion by trying to solve one of the deepest problems in physics, and that problem emerged from studying the strangest objects in the universe, black holes. To understand why black holes led us to the Holographic Universe Theory, I need to take you on a journey through one of the most exciting periods in the history of physics. It is a story of brilliant minds clashing, of paradoxes that seemed unsolvable, and of discoveries that changed everything we thought we knew about the nature of information, reality, and existence itself. Let us start with the basics. What exactly is a black hole? A black hole is what you get when matter becomes so incredibly dense that its gravitational pull becomes inescapable. Not even light, the fastest thing in the universe, can escape from a black hole. That is why they are called black. They emit no light of their own. They are literally holes in the fabric of space-time. Black holes form when massive stars die. Throughout its life, a star is in a constant battle between two forces. Gravity wants to crush the star inward, while the nuclear fusion reactions at the star's core push outward. It is like a cosmic tug-of-war that lasts millions or billions of years. But eventually the star runs out of fuel. When this happens to a star much more massive than our Sun, gravity wins the battle catastrophically. The core of the star collapses in on itself with tremendous force. If the star is massive enough, this collapse continues without stopping. The matter gets denser and denser, the gravitational field gets stronger and stronger, until something extraordinary happens. The escape velocity, the speed you would need to escape the gravitational pull, exceeds the speed of light. At this point, nothing can escape. A black hole is born. The boundary around a black hole from which nothing can escape is called the event horizon. This is not a physical surface. You would not feel anything special as you crossed it, but it is a point of no return. Once you cross the event horizon, your fate is sealed. You will inevitably be pulled toward the center of the black hole, toward a point of infinite density called the singularity. At the singularity, our current understanding of physics breaks down completely. We do not know what happens there because the equations give us infinities, which is usually a sign that our theories are incomplete. For most of the 20th century, black holes were considered theoretical curiosities. Even Einstein, whose theory of general relativity predicted their existence, did not believe they could actually form in nature. But observations eventually proved that black holes are very real. We now know that supermassive black holes, millions or billions of times the mass of our Sun, sit at the centers of most galaxies, including our own Milky Way. Black holes are not rare, they are fundamental components of the cosmic architecture. Now here is where our story gets really interesting. In the early 1970s, a young physicist named Stephen Hawking started thinking about what would happen if you applied quantum mechanics to black holes. Quantum mechanics is the physics of the very small, the realm of atoms and subatomic particles. General relativity, which describes black holes, is the physics of the very large, the realm of stars and galaxies. These two theories are notoriously difficult to combine. They use different mathematical frameworks and make different assumptions about reality. But Hawking realized that near the event horizon of a black hole, where gravity is incredibly strong, quantum effects should become important. What Hawking discovered in 1974 shocked the physics world. He calculated that black holes are not completely black. They actually emit radiation. This radiation, now called Hawking radiation, is incredibly faint. A black hole with the mass of our Sun would emit so little Hawking radiation that it would be completely undetectable. But the implications were profound. If black holes emit radiation, they are losing energy. And if they are losing energy, they are slowly evaporating. Given enough time, unfathomably long periods of time, trillions upon trillions of years, a black hole will completely evaporate away until nothing remains. This was already a revolutionary discovery, but Hawking quickly realized something even more disturbing. As a black hole evaporates, what happens to all the information that fell into it? Now I need to explain what physicists mean by information because it is not quite the same as what we mean in everyday language. In physics, information refers to the complete quantum state of a system, all the details about every particle, their positions, momenta, spins, and all other quantum properties. According to the fundamental laws of quantum mechanics, information cannot be destroyed. It can be scrambled, mixed up, and made practically impossible to retrieve, but it cannot be truly lost. This is called unitarity, and it is one of the foundational principles of quantum mechanics. Here is the problem. Hawking calculated that the radiation emitted by black holes is thermal radiation. It is completely random, like the heat radiating from a warm object. It carries no information about what fell into the black hole. If you throw a book into a black hole, the information in that book, every word, every letter, every arrangement of atoms, should theoretically be encoded somewhere. But according to Hawking's calculations, when the black hole eventually evaporates, all that remains is random thermal radiation. The information in the book appears to be genuinely lost, erased from the universe forever. This is the black hole information paradox, and it represents one of the deepest crises in theoretical physics. If Hawking is right and information is truly destroyed in black holes, then quantum mechanics is wrong. The fundamental laws that govern atoms and particles, the laws that have been tested and verified to incredible precision, would be violated. But if quantum mechanics is right and information must be preserved, then something about Hawking's calculation must be missing. We need to find where the information goes. This paradox launched what Leonard Susskind later called the Black Hole War. It was not a war with weapons, but a war of ideas, fought with mathematics and physical reasoning. On one side was Stephen Hawking, arguably the most famous physicist since Einstein, who maintained that information was genuinely destroyed. On the other side were Leonard Susskind, Gerard de Hooft, and a growing number of physicists who believed that information must somehow survive, even if we did not yet understand how. The stakes could not have been higher. This was not an obscure technical disagreement. This was about the fundamental nature of reality. Either quantum mechanics was wrong, or our understanding of black holes was incomplete, or there was something deeply strange about the universe that we had not yet discovered. The answer, when it finally emerged, was stranger than anyone had imagined. Before the full resolution came, there was a crucial intermediate discovery that planted the seed of everything that followed. In the early 1970s, a physicist named Jacob Bekenstein asked a simple question. Do black holes have entropy? Entropy is a measure of disorder, or more precisely, a measure of the number of different microscopic arrangements that could give rise to the same macroscopic state. A cup of hot coffee has high entropy because there are countless ways the water molecules could be arranged while still giving you a cup of hot coffee. A perfectly ordered crystal has low entropy because there are very few ways to arrange the atoms while maintaining the perfect crystal structure. Bekenstein proposed that black holes must have entropy. The second law of thermodynamics says that the total entropy of the universe always increases. If you could throw a high entropy object into a black hole and have it disappear completely, the total entropy of the universe would decrease. This would violate the second law of thermodynamics, one of the most fundamental laws in all of physics. So Bekenstein argued that black holes must have their own entropy, and when something falls in, that entropy is added to the black hole's entropy. But here is the strange part. Bekenstein calculated how much entropy a black hole has, and he found something very surprising. The entropy of a black hole is proportional to its surface area, not its volume. Think about how weird this is. If you have a box of gas, the entropy depends on the volume of the box. More volume means more room for particles to be arranged in different ways, which means more entropy. You would expect the same for black holes. A bigger black hole should have more entropy because it has more volume for stuff to be inside it. But that is not what Bekenstein found. The entropy depends only on the surface area of the event horizon. This was the first major clue that something very strange is going on with black holes and information. If the entropy, which measures how much information the black hole contains, is proportional to the surface area rather than the volume, then maybe the information is somehow stored on the surface, not in the interior. Let me make sure you understand why this is so remarkable. Imagine you have a library full of books. You would expect that a bigger library can hold more books, more information. The amount of information scales with the volume. But Bekenstein's calculation says that for black holes, the amount of information scales with the walls of the library, not the floor space. A black hole's information storage capacity is determined by its surface, not its interior. This is deeply counterintuitive, and it hinted at a profound truth about the nature of space and information. Now we arrive at the revolutionary leap. In 1993, Gerard de Hooft, a Dutch physicist who would later win the Nobel Prize, proposed something radical. He suggested that what we found for black holes might be true for the entire universe. Maybe all the information in any region of space can be described entirely by information on the boundary of that region. Maybe the three-dimensional world we see is actually encoded on a two-dimensional surface. Maybe the universe is a hologram. Hooft called this the holographic principle, and when he first proposed it, many physicists thought he had lost his mind. It seemed too crazy, too speculative, too far removed from anything we could test. But Leonard Susskind took the idea seriously and developed it into a more rigorous framework. Susskind had been fighting the black hole war for years, trying to prove that information is not destroyed in black holes. He realized that the holographic principle might be the key to solving the puzzle. Let me explain the holographic principle more carefully because this is the heart of everything. The principle states that all the information contained within a volume of space can be represented as information on the boundary of that volume. Think of it this way. Imagine you have a room, a three-dimensional space. According to the holographic principle, everything that happens in that room, every object, every movement, every interaction, can be completely described by information encoded on the walls, floor, and ceiling of the room, the two-dimensional boundary. The three-dimensional interior is somehow a projection or reconstruction from the two-dimensional boundary. This is exactly like a hologram. Remember how a hologram works. A three-dimensional information about an object is encoded in a two-dimensional interference pattern on a flat surface. When light shines through the hologram, the three-dimensional image is reconstructed. The holographic principle says the universe works the same way. The three-dimensional universe we experience is reconstructed or projected from information encoded on a distant two-dimensional surface, perhaps at the cosmic horizon at the edge of the observable universe. Now you might be thinking, okay, this is a wild hypothesis, but is there any actual evidence for it? This is where our story takes an extraordinary turn. In 1997, a young Argentinian physicist named Juan Maldacena, working at Harvard, published a paper that would become the most cited paper in the history of high-energy physics. What Maldacena discovered was nothing short of miraculous. He found a concrete mathematical example where the holographic principle is provably true. Maldacena's discovery is called the ADS/CFT correspondence. Let me break this down for you. ADS stands for anti-de Sitter space, which is a particular type of curved spacetime with negative curvature. It is not the same as our universe, which has positive or zero curvature, but it is mathematically tractable and shares many important features with real physics. CFT stands for conformal field theory, which is a special type of quantum field theory that lives on the boundary of the ADS space. What Maldacena proved is that a theory of gravity in a five-dimensional ADS space is exactly equivalent to a conformal field theory without gravity on the four-dimensional boundary. Let me say that again because it is so important. A universe with gravity in 5 dimensions is the same as a universe without gravity in 4 dimensions. They are not approximately the same. They are not similar. They are mathematically identical. Every calculation you can do in the 5-dimensional theory with gravity gives you the same answer as a corresponding calculation in the 4-dimensional theory without gravity. This is the holographic principle made mathematically precise. A higher dimensional space with gravity is equivalent to a lower dimensional space without gravity on its boundary. The boundary theory is like a hologram that contains all the information of the higher dimensional bulk space. You can think of the higher dimensional universe as being projected from or encoded in the lower dimensional boundary. Maldacena's discovery was not just a theoretical curiosity, it became an incredibly powerful tool for physics. There are many problems in gravitational physics that are extremely difficult to solve, but using the ADS/CFT correspondence, you can translate these problems into equivalent problems in the boundary theory, which is often much easier to solve. Physicists have used this technique to make progress on problems that seemed intractable for decades. But what does this mean for our universe? Here is the honest answer. Our universe is not an anti-de Sitter space. Our universe has positive cosmological constant and is expanding, while ADS space has negative cosmological constant and is not like our universe at all. So Maldacena's result does not directly prove that our universe is a hologram. However, it provides an existence proof. It shows that holographic universes are mathematically possible and consistent. It demonstrates that the crazy-sounding idea of higher dimensional reality being encoded on lower dimensional boundaries is not just speculation. It actually works in at least some cases. Many physicists believe that our universe probably has some version of holographic description, even if we have not yet figured out exactly what it is. The universe seems to be telling us something deep about the relationship between dimensions, information, and reality. And the fact that the holographic principle naturally resolves the black hole information paradox makes it even more compelling. Let me explain how holography solves the information paradox. If the information that falls into a black hole is actually encoded on the event horizon, the two-dimensional surface surrounding the black hole, then the information was never inside the black hole in the traditional sense. It was always on the surface. When the black hole evaporates via Hawking radiation, the information can escape because it was always on the boundary, not in the interior. The apparent destruction of information was an illusion, caused by our incorrect assumption that information was stored in the three-dimensional interior. Susskind developed this idea further with something called black hole complementarity. He proposed that if you are falling into a black hole, you would see information falling in with you into the interior, but if you are observing from outside, you would see the information spread across the event horizon. Both descriptions are correct, but you can never be in a position to observe both simultaneously. The information is both inside and on the surface, depending on your perspective. This sounds contradictory, but it is actually consistent because no single observer can verify both descriptions. Now, I want to take you deeper into the quantum mechanical aspects of holography, because this is where things get really strange and really beautiful. Quantum mechanics has already shown us that reality at the fundamental level is nothing like our everyday experience. Particles can be in multiple places at once, a phenomenon called superposition. Particles can be instantaneously connected across vast distances, a phenomenon called entanglement. The act of observation seems to affect what we observe, the measurement problem. Quantum mechanics paints a picture of reality that is fuzzy, probabilistic, and deeply interconnected. Quantum entanglement is particularly relevant to our discussion. When two particles become entangled, their quantum states become correlated in a way that cannot be explained by classical physics. If you measure a property of one entangled particle, you instantly know something about its partner, even if the partner is on the other side of the universe. Einstein famously called this spooky action at a distance and thought it proved quantum mechanics must be incomplete. But countless experiments have confirmed that entanglement is real. The correlations are there, and they cannot be explained by any local hidden variables. In 2010, physicist Mark van Ramsdonk proposed something extraordinary. He suggested that the fabric of space-time itself, the very stage on which the drama of the universe unfolds, might emerge from quantum entanglement. This was a radical idea. We usually think of space-time as the fundamental background, and quantum fields as things that exist within space-time. But Van Ramsdonk proposed inverting this picture. Quantum entanglement is fundamental, and space-time emerges from it. Van Ramsdonk studied the ADS/CFT correspondence and found something remarkable. In the boundary theory, the CFT, there is no gravity and no traditional space-time in the interior of ADS, but there is quantum entanglement between different regions of the boundary. Van Ramsdonk found that the amount of entanglement between two regions of the boundary corresponds to the connectedness of space-time in the bulk. Regions that are highly entangled in the boundary theory are connected by smooth space-time in the bulk. If you reduce the entanglement, the space-time connection weakens. If you remove the entanglement entirely, the space-time tears apart. This leads to a stunning conclusion. Space-time is stitched together by quantum entanglement. The smooth, continuous, three-dimensional or higher-dimensional space we seem to inhabit is not fundamental. It emerges from the pattern of quantum entanglement in a lower-dimensional system. Space itself is a projection, a hologram, created by the web of quantum correlations on the boundary. This idea was further developed with the ER=EPR conjecture, proposed by Maldacena and Susskind in 2013. ER refers to Einstein-Rosen bridges, which are better known as wormholes, hypothetical tunnels through space-time connecting distant regions. EPR refers to Einstein-Podolsky-Rosen correlations, which is the old name for quantum entanglement. The conjecture says that these two phenomena, wormholes and entanglement, are actually the same thing. Every pair of entangled particles is connected by a tiny wormhole, and every wormhole is a manifestation of entanglement. If this is true, then the universe is far more interconnected than we ever imagined. Every entangled pair of particles has a tiny wormhole between them. The quantum vacuum is crisscrossed by countless microscopic wormholes connecting entangled particles throughout space-time, and all of this structure emerges from patterns of information on a lower dimensional boundary. Let me pause here and help you appreciate how remarkable this is. We started with a simple question about what happens to information when it falls into a black hole. We ended up with a picture of reality where space-time itself is not fundamental. Space is a holographic projection, emerging from quantum entanglement patterns on a distant boundary. Three-dimensional reality is encoded in two dimensions. The solid, continuous space we think we move through is woven from the ghostly threads of quantum correlations. But wait, you might ask, is there any evidence for any of this? Can we actually test whether the universe is a hologram? This is a crucial question, and the honest answer is that we do not yet have definitive proof. However, there are intriguing hints and ongoing experiments that might eventually provide evidence. The most tantalizing observational hint came from studies of the cosmic microwave background radiation. The CMB is the afterglow of the Big Bang, light that has been traveling through space for nearly 14 billion years. It is the oldest light in the universe, and it provides a snapshot of what the universe looked like when it was just 380,000 years old. The CMB is incredibly smooth, with tiny temperature fluctuations of about 1 part in 100,000. These fluctuations are the seeds from which all the galaxies, stars, and planets eventually grew. In 2017, a team of physicists led by Niyesha Afshori analyzed the CMB data looking for signatures that might be expected if the universe is holographic. They examined the pattern of fluctuations and compared them to predictions from both standard cosmology and holographic models. Remarkably, they found that certain holographic models fit the data as well as, or in some cases better than, standard models. This is not proof that the universe is a hologram, but it shows that holographic cosmology is a serious scientific theory that makes testable predictions consistent with observations. There have also been attempts to directly detect evidence of holographic structure at the smallest scales. If space is fundamentally grainy and holographic, there should be tiny fluctuations at the Planck scale, the smallest meaningful length scale in physics. Craig Hogan, a physicist at Fermilab, proposed that these fluctuations might manifest as a kind of holographic noise in precision experiments. Hogan built an instrument called the holometer specifically to search for this holographic noise. The holometer uses highly sensitive laser interferometry, similar to the technology used to detect gravitational waves, to look for correlated noise that would be a signature of holographic spacetime. The experiments ran for several years, and the results were published in 2015. Unfortunately, the holometer did not detect the predicted holographic noise at the levels Hogan had expected. Does this disprove the holographic universe? Not necessarily. The null result means that if holographic noise exists, it is smaller than what the holometer could detect, or it might manifest differently than Hogan predicted. The holographic principle is a broad framework that can be implemented in many different ways, and ruling out one specific prediction does not rule out the general idea. Can other experiments continue to search for different signatures of holographic physics? The Event Horizon Telescope, which produced the first image of a black hole in 2019, provides another avenue for testing holographic ideas. By studying the detailed properties of black hole horizons, physicists hope to test predictions about information encoding on the horizon. Future observations with improved resolution might reveal signatures consistent with, or incompatible with, holographic models. There is also the theoretical consistency argument. The holographic principle provides the only known resolution to the black hole information paradox that preserves quantum mechanics. It emerges naturally from string theory, which is currently our best candidate for a unified theory of physics. The mathematical framework of ADS/CFT is incredibly rich and has led to numerous successful predictions and calculations. This does not prove that the universe is a hologram, but it suggests that holographic ideas capture something true about the deep structure of reality. Now let us step back and consider the philosophical implications of all this. If the universe is indeed a hologram, what does that mean for us? What does it mean for reality, for consciousness, for the meaning of existence? First, I want to address a common misconception. When people hear that the universe might be a hologram, they often think it means the universe is fake or unreal, like a simulation running on some cosmic computer. But that is not what physicists mean by a holographic universe. The holographic principle says that a complete description of reality can be given in terms of a lower dimensional surface. It does not say that one description is more real than the other. Think about it this way. You can describe a cube as a three-dimensional object, or you can describe it using two-dimensional blueprints that specify its shape from different angles. Both descriptions are complete and accurate. Neither is more real than the other. They are just different representations of the same underlying reality. Similarly, if the universe is holographic, there are equivalent descriptions in different numbers of dimensions. But this does not make any of them fake or illusory. In fact, there is a profound sense in which a holographic universe is more real, not less. In a holographic universe, the three-dimensional reality we experience is robust and protected. Because the information is encoded on a two-dimensional surface in a non-local way, like how cutting a hologram in half still preserves the whole image, the three-dimensional reality that emerges is incredibly stable. It is not fragile or easily disrupted. The holographic encoding is like a cosmic error correction code that ensures the consistency and stability of the projected reality. But there is still something philosophically significant about the holographic universe. It challenges our intuitive sense of what is fundamental. We naturally think that the three-dimensional space we see and move through is the fundamental stage on which reality plays out. But if the holographic principle is correct, three-dimensional space is not fundamental at all. It is emergent and derived from something more basic. The true fundamental description might be in terms of information, quantum entanglement, and lower dimensional structures that we cannot directly perceive. This connects to an ancient philosophical tradition that views the everyday world as somehow illusory or secondary to a deeper reality. Plato's allegory of the cave described ordinary perception as like watching shadows on a wall, mistaking these shadows for ultimate reality, while the true forms exist in a realm we cannot directly see. Hindu philosophy speaks of Maya, the cosmic illusion that makes us mistake the phenomenal world for the ultimate reality of Brahman. Buddhist teachings emphasize that our ordinary perception is clouded by ignorance and attachment, and that enlightenment involves seeing through these illusions to the true nature of existence. I'm not suggesting that ancient philosophers somehow knew about holography, or that their metaphors should be taken literally. But there is a resonance between these traditions and modern physics. Both suggest that the reality we ordinarily perceive is not the deepest level of existence, that there is something more fundamental underlying appearances, and that understanding this deeper level can transform our relationship to the world. The holographic principle also connects to questions about consciousness and the nature of mind. If information is fundamental, if the universe at its deepest level is best described not in terms of matter and energy, but in terms of bits and quantum states, then consciousness, which is fundamentally about information processing, might not be as mysterious as it seems. Some philosophers have proposed that consciousness might be a fundamental feature of information processing systems, that wherever information is integrated and processed in sufficiently complex ways, there is some form of experience. This view, called panpsychism or integrated information theory, does not require a holographic universe, but it fits naturally with the picture of reality as fundamentally informational. If the universe is a holographic encoding of information, and if consciousness arises from information processing, then consciousness is woven into the very fabric of cosmic existence. We are not alien to the universe, somehow separate from the physical processes around us. We are expressions of the same fundamental informational structure that underlies all of reality. Of course, these are speculations, not established science. We do not yet have a theory that explains how consciousness arises from physical processes, holographic or otherwise. The hard problem of consciousness, as philosopher David Chalmers called it, remains unsolved. But the holographic universe provides a framework within which we can think about these questions in new ways. Now I want to address the relationship between the holographic universe and another idea you have probably heard of, the simulation hypothesis. The simulation hypothesis, popularized by philosopher Nick Bostrom and by Elon Musk, proposes that we might be living in a computer simulation created by an advanced civilization. At first glance, this might seem similar to the holographic universe. Both suggest that reality is somehow not what it appears, but there are crucial differences. The simulation hypothesis requires a simulator, an advanced intelligence that created and runs the simulation. It is essentially a technological hypothesis about the origin of our universe. The holographic principle, by contrast, does not require any external creator or computer. It is a natural property of how physics works. If the universe is holographic, it is because the laws of physics have a holographic structure, not because someone designed it that way. Another difference is testability. The simulation hypothesis is extremely difficult to test because a sufficiently advanced simulator could presumably hide any evidence of the simulation. The holographic principle, by contrast, almost makes specific predictions about things like the entropy of black holes, correlations in the cosmic microwave background, and the mathematical structure of quantum gravity. These predictions can in principle be tested, and many have already been confirmed. So while both ideas challenge our naive view of reality, they're quite different in their implications and scientific status. The holographic universe is a serious scientific hypothesis with mathematical foundations and growing empirical support. The simulation hypothesis is more of a philosophical thought experiment without comparable scientific backing. Let me also address the critics and skeptics of the holographic principle, because good science requires considering counterarguments. Some physicists argue that the holographic principle, while mathematically elegant, may be just a useful computational tool rather than a literal description of reality. After all, we have other examples in physics where different mathematical descriptions are equivalent, but it does not make sense to say one is more real than another. Others point out that the best understood example of holography, ADS/CFT, applies to a type of spacetime very different from our own universe. Extending holographic ideas to our actual universe is speculative and fraught with technical difficulties. We do not have a proven holographic description of cosmology or of de Sitter space, which better describes our expanding universe. There is also the concern that some holographic ideas, particularly when combined with string theory, have become so far removed from experiment that they risk being not even wrong. As physicist Wolfgang Pauli supposedly said about untestable theories, if a theory cannot be tested even in principle, is it still science? These are legitimate concerns, and physicists who work on holography take them seriously. The response is generally that the holographic principle has been too successful to dismiss. It solves the black hole information paradox in a way that no other approach has managed. It has mathematical backing that is extraordinarily robust. And while we do not yet have a holographic description of our exact universe, the direction of progress suggests that one might be possible. Science is always provisional. Our best theories are always subject to revision in light of new evidence. The holographic principle may turn out to be profoundly true, partly true or completely wrong, but right now, it represents one of our deepest insights into the fundamental nature of reality, and it deserves to be taken seriously. Let me now tell you about where this research is heading and what we might learn in the coming years. Holography has become one of the most active areas of theoretical physics. Thousands of papers are published every year exploring various aspects of the holographic principle and its applications. Researchers are working on extending holographic ideas to cosmology, to condensed matter physics, to quantum information theory, and to many other areas. One of the most exciting frontiers is the connection between holography and quantum information. Researchers have discovered that the holographic encoding of information on boundaries is related to quantum error correction, the techniques used to protect information in quantum computers. This suggests deep connections between gravity, space-time, and quantum computing that we're only beginning to understand. Another frontier is the study of quantum chaos and scrambling, how information becomes spread out and effectively hidden in quantum systems. Black holes appear to be the fastest scramblers in nature, hiding information almost instantaneously. Understanding this process is crucial for resolving the information paradox and for understanding the holographic nature of space-time. There is also ongoing work on extending holography beyond ADS space to more realistic cosmological settings. While this is technically challenging, there have been promising developments. Some researchers have proposed variants of holography that might apply to de Sitter space, as the type of space-time that better describes our universe. Others are exploring the possibility that our universe has some kind of dual boundary description, even if it is different from the simple boundaries in ADS/CFT. Experimental tests continue as well. Future gravitational wave detectors will be more sensitive and might detect signatures related to the quantum structure of spacetime and black hole horizons. Future CMB observations might provide more detailed tests of holographic cosmological models, and while the holometer did not find the expected holographic noise, refined experiments with different designs might succeed. We're also likely to see progress from quantum computers. As quantum computers become more powerful, they will be able to simulate quantum systems with gravity, allowing us to test holographic predictions in controlled settings. This might not tell us directly whether our universe is holographic, but it will let us explore the mathematics of holography in unprecedented detail. Now, I want to bring all of this together and help you see the big picture. We have covered a lot of ground, from ordinary holograms to black holes, to the deepest questions about the nature of reality. Let me summarize what we have learned. It all started with black holes, and the discovery that they have entropy proportional to their surface area, not their volume. This was the first hint that information in the universe might be stored on boundaries rather than in bulk volumes. Then came the black hole information paradox. the realization that information seemed to be destroyed when black holes evaporate, violating fundamental principles of quantum mechanics. The resolution of this paradox led to the holographic principle, the proposal that all information in any region of space can be described by information on the boundary of that region. This wild-sounding idea was put on rigorous mathematical footing by Maldacena's ADS/CFT correspondence, which proved that a universe with gravity in 5 dimensions is exactly equivalent to a universe without gravity in 4 dimensions on its boundary. This was the holographic principle made precise. Further research revealed that space-time itself might emerge from quantum entanglement, that the smooth fabric of space is woven from quantum correlations. The implications are profound. The 3-dimensional reality we experience may not be fundamental. It may be a projection, a holographic reconstruction from information encoded on a distant 2-dimensional surface. Space itself may be emergent, arising from more fundamental quantum information. The universe, in a deep sense, may be made of information rather than matter. We have also seen that there is evidence, though not yet proof, supporting holographic cosmology. The mathematics works beautifully. It solves deep puzzles. It provides new tools for calculation. And observations of the cosmic microwave background and black holes are at least consistent with holographic models. What does this mean for you? How should you live differently, knowing that the universe might be a hologram? Honestly, I think the most profound effect should be a sense of wonder and humility. We are tiny creatures on a small planet in an ordinary galaxy, yet we have managed to glimpse something profound about the nature of existence. The universe is stranger and more beautiful than we could have imagined. The reality we experience is a thin surface over depths we are only beginning to fathom. It should also remind us that our intuitions about reality are not reliable. We evolved to survive on the African savanna, not to understand quantum gravity. Our brains give us useful representations of reality, not accurate ones. When physics tells us something counterintuitive, we should take it seriously, even when it challenges our deepest assumptions about space, time, and existence. And perhaps most importantly, the holographic universe reminds us that everything is connected. The information that makes up your body is entangled with information across the cosmos. The space between us is woven from the same quantum threads that connect distant galaxies. We are not separate from the universe. We are expressions of it, temporary patterns in the cosmic hologram, experiencing itself. I want to leave you with one final thought. Throughout human history, we have repeatedly discovered that the universe is not what it appears to be. The Earth seemed flat and stationary, but it turned out to be a spinning sphere hurtling through space. Matter seemed solid and continuous, but it turned out to be mostly empty space with tiny particles held together by forces. Time seemed absolute and universal, but it turned out to be relative, flowing differently for different observers. And now, perhaps, the 3-dimensional space we inhabit is turning out to be a holographic projection from a distant 2-dimensional surface. Each of these discoveries was disorienting at first. Each challenged our sense of reality. But each also opened new horizons of understanding and revealed unsuspected depths to existence. The holographic universe, if true, would be the latest and perhaps greatest of these revelations, showing us that the very fabric of space is not what we thought, that reality itself is stranger and more wonderful than our wildest dreams. We do not yet know for certain whether the universe is a hologram. The evidence is suggestive but not conclusive. The mathematics is beautiful but applies most directly to space-times different from our own. The experiments continue, and the answer may take decades or centuries to emerge. But here is what I believe. Whether or not the universe turns out to be literally holographic, the holographic principle has revealed something true about the deep structure of reality. Information is more fundamental than we realized. Boundaries encode more than we expected. Dimensions are not as absolute as they seemed. These insights will endure even if the specific holographic hypothesis needs to be modified. And that, to me, is the beauty of science. We ask questions, we propose answers, we test them against reality. Sometimes we are right, sometimes we are wrong, but we're always learning, always peeling back another layer of the cosmic onion, always getting closer to the truth. If this video has changed how you think about reality, if it has sparked your curiosity about the universe you inhabit, then I have accomplished what I set out to do. The universe gave you a mind capable of contemplating its own nature. Use that gift. Keep questioning. Keep wondering. Keep looking up at the stars and asking what lies beyond. Now I have a question for you. After watching this entire video, after learning about black holes and entropy and the holographic principle and quantum entanglement, do you think the universe is a hologram? Has your view changed from what you commented at the beginning? Let me know in the comments below. I read every single comment and I am genuinely curious what you think. If you found this video valuable, please give it a like. It helps the algorithm show this content to other curious minds. Share it with someone who loves to think about the big questions. And if you have not subscribed yet, this is your sign. Subscribe and hit the notification bell so you do not miss future explorations of the deepest mysteries of space, time, and existence. Thank you for joining me on this journey through one of the strangest and most beautiful ideas in all of physics. The universe is full of wonders waiting to be discovered, and every time we discover something new, we find that reality is more amazing than we ever imagined. Until next time, keep looking up and keep asking why. We have traveled through the cosmic rabbit hole together, from the mundane physics of credit card holograms to the mind-bending mathematics of higher dimensional spacetimes. We have seen how black holes guard secrets about the fundamental nature of information. We have watched as brilliant physicists fought intellectual battles over paradoxes that seem to break physics itself. And we have arrived at a picture of reality that would have seemed like madness just a few decades ago, but now stands as one of the most rigorous and well-supported ideas in theoretical physics. But there is still so much more to explore. The holographic principle opens doorways to other profound questions that we have only touched upon. Let me take you deeper into some of these rabbit holes, because the more you understand, the more extraordinary the universe becomes. Let us talk about the nature of time in a holographic universe. We are so accustomed to thinking of time as flowing inexorably forward, carrying us from past through present into future. But in a holographic universe, time might be very different from what we assume. If all the information about our four-dimensional space-time, including all of its temporal evolution, is encoded on a three-dimensional or even two-dimensional boundary, then in some sense, all of time might exist simultaneously on that boundary. The flow of time that we experience might be an emergent phenomenon, something that appears from the inside of the hologram but is not fundamental to the underlying description. This connects to the long-standing debate in physics between the block universe view, where past, present, and future all exist equally, and the presentist view, where only the present moment is real. The holographic principle seems to favor something like the block universe. If the complete description of reality is a static encoding on a boundary, then temporal evolution is just how things appear from inside the hologram, not a fundamental feature of the deepest level of description. Think about what this means for questions of fate and free will. If all of time is already encoded on the cosmic boundary, does that mean your future is already determined? Not necessarily. The holographic encoding might include all possible quantum futures in superposition. From the boundary perspective, every possible version of your life might be equally real, and what you experience as choice might be the process of actualizing one path through this vast space of possibilities. This is speculative, of course, but it shows how holography connects to questions philosophers have debated for millennia. Let us also dive deeper into the connection between holography and quantum computing, because this is one of the most exciting frontiers of current research. Quantum computers exploit the strange properties of quantum mechanics, such as superposition and entanglement, to perform calculations that would be impossible for classical computers. It turns out that the way information is encoded holographically has deep connections to the error correction codes used in quantum computing. In a classical computer, information is stored in bits, each of which is either 0 or 1. If a bit gets corrupted, the information is lost. Classical error correction works by storing redundant copies of information, so if one copy is corrupted, the others can be used to recover the original. Quantum error correction is far more subtle, because quantum information cannot simply be copied, a fundamental result known as the no-cloning theorem. Quantum error correction works by encoding quantum information in complex entanglement patterns spread across many qubits. If a few qubits get corrupted, the information can still be recovered from the pattern of entanglement in the remaining qubits. This is remarkably similar to how holograms work. Remember, if you cut a hologram in half, each piece still contains the complete image, just at lower resolution. the information is spread non-locally throughout the hologram. Researchers have discovered that the holographic encoding of bulk spacetime information on the boundary follows the same mathematical structure as certain quantum error correction codes. This is not just an analogy, the mathematics is identical. The boundary theory literally implements a quantum error correction code that encodes the bulk spacetime. This has profound implications. It suggests that spacetime itself is a kind of quantum error correction code, a way of encoding quantum information in a robust, distributed manner. The geometry of spacetime emerges from the structure of this code. The distance between points in the bulk spacetime is related to how the information is distributed in the boundary code. This connects to another deep question. Why does spacetime exist at all? Why do we experience a smooth, continuous, three-dimensional space rather than some other kind of existence? The holographic perspective suggests an answer. Spacetime is the natural structure that emerges when quantum information is encoded in a particular way. It is not that information exists in spacetime. It is that spacetime is a consequence of how information is organized. Let me take you even further down the rabbit hole into the question of what the boundary actually is. In the ADS/CFT correspondence, the boundary is a well-defined mathematical surface at the edge of anti-de Sitter space. But what about our universe? If our universe is holographic, where is the boundary? One possibility is that the boundary is at the cosmological horizon, the edge of the observable universe. Light from beyond the cosmological horizon has not had time to reach us since the Big Bang, so we cannot see or interact with anything beyond it. This horizon could be where the holographic information is encoded. Another possibility is that the boundary is in the distant past or future. Some researchers have proposed that the information about our universe is encoded on the surface at the Big Bang or at the heat death of the universe. In this picture, all of cosmic history is a holographic projection from a boundary at the temporal edge of existence. There are even more exotic possibilities. Some physicists have suggested that every surface in the universe might serve as a holographic boundary for the region inside it. In this fractal holography picture, holographic encoding happens at every scale, from the cosmic horizon down to the smallest black holes. The universe is holographic all the way down. These are all speculative ideas, and we do not yet know which, if any, is correct. But they show the richness of the holographic framework and the many directions research can take. Now let us address something that many people wonder about when they hear about the holographic universe. If reality is a hologram, does that mean there is something outside the hologram? Is there a more real reality that exists beyond the holographic surface? This is a natural question, but it might be based on a misconception. In the holographic framework, the boundary description and the bulk description are equivalent. Neither is more real than the other. They are just different ways of describing the same underlying reality. It is not that one is the simulation and the other is the real thing. Both are equally valid descriptions. Think of it like coordinate systems in mathematics. You can describe a point in space using Cartesian coordinates, or spherical coordinates, or any number of other systems. The point is the same regardless of how you describe it. The coordinate system is just a tool for representation. Similarly, the holographic boundary description and the bulk spacetime description might just be different coordinate systems, different representations of the same underlying reality. However, there is a sense in which the holographic perspective does suggest that something is more fundamental than everyday three-dimensional space. That something is information, or more precisely quantum information, and its entanglement structure. The geometry of spacetime emerges from this more fundamental layer, so while there may not be something outside the hologram, there is something beneath it, a level of description more basic than space and time. This brings us to the deep question of what reality ultimately is. Is the universe made of matter and energy, as we commonly assume? Is it made of space-time, the arena within which matter and energy exist? Or is it made of information, with matter, energy, and space-time all emerging from more fundamental informational structures? The holographic principle suggests the last option. At the deepest level, the universe might be pure information, organized according to principles we're only beginning to understand. The physical world we experience with its objects and forces and spaces might be emergent phenomena arising from the underlying information. This resonates with something the great physicist John Wheeler said late in his life. Wheeler was one of the most important physicists of the 20th century, who among other things coined the term black hole and supervised Richard Feynman's doctoral thesis. In his later years, Wheeler proposed the idea of it from bit, suggesting that every physical quantity, every particle and field and space-time interval, derives its meaning and existence from information-theoretic yes or no questions. Reality, Wheeler suggested, is fundamentally informational. The holographic principle can be seen as a concrete realization of Wheeler's vision. If all the information about bulk spacetime is encoded on a lower dimensional boundary, then information is primary and spacetime is derived. It from bit. Let me also discuss the connection between holography and the search for quantum gravity. One of the great unsolved problems in physics is how to combine quantum mechanics with general relativity. Quantum mechanics describes the physics of the very small, where particles behave probabilistically and exist in superpositions. General relativity describes the physics of the very large, where massive objects curve spacetime and create gravity. Both theories are incredibly successful within their domains, but they are mathematically incompatible. When you try to apply quantum mechanics to the gravitational field, you get nonsense, infinite results that cannot be renormalized. String theory was developed partly to solve this problem. In string theory, the fundamental objects are not point particles, but tiny vibrating strings. These strings have different vibrational modes, and each mode corresponds to a different particle. Remarkably, one of these modes corresponds to the graviton, the particle that carries the gravitational force. String theory automatically includes gravity in a quantum mechanical framework. The holographic principle emerged from string theory and provides a new way to think about quantum gravity. In the ADS/CFT correspondence, the boundary theory is a quantum field theory without gravity, which we understand very well. The bulk theory is a theory of quantum gravity, which we understand poorly. The holographic correspondence lets us translate questions about quantum gravity into questions about quantum field theory, which we can then answer. This has led to enormous progress in understanding quantum gravity. We have learned about the entropy of black holes, the information paradox, the emergence of spacetime, and many other deep questions. While we do not yet have a complete theory of quantum gravity, holography has given us crucial insights and mathematical tools. The holographic principle also suggests a resolution to another deep puzzle: why gravity is so much weaker than the other forces of nature. The electromagnetic force between two electrons is about 10 to the 40 times stronger than the gravitational force between them. This huge discrepancy is called the hierarchy problem, and it has puzzled physicists for decades. One possible resolution involves extra dimensions. If space has more dimensions than the three we observe, gravity might propagate through all of them, while other forces are confined to a three-dimensional brane, a lower dimensional surface embedded in the higher dimensional space. This would dilute gravity's strength in our three-dimensional world, explaining its weakness. The holographic principle provides a complementary perspective. If the three-dimensional world we inhabit is a projection from a lower dimensional boundary, the relationship between dimensions is fundamentally different from what we assumed. The hierarchy problem might dissolve in a holographic framework because the very notion of dimension becomes more fluid and less fundamental. Now let us consider some of the more speculative implications of the holographic universe. If information is fundamental and spacetime is emergent, what does that mean for the possibility of traveling to other dimensions or other universes? In science fiction, travel to other dimensions usually involves finding some kind of doorway or portal that leads to a parallel reality. The holographic principle suggests a different picture. Different dimensional descriptions might not be different places you could travel to, but different ways of viewing the same reality. You cannot travel from the bulk to the boundary, because they are the same thing described differently. However, the holographic principle does leave room for more exotic possibilities. If our universe is one holographic projection from a particular boundary, there might be other boundaries projecting other universes. In the string theory landscape, there are countless possible ways to configure the extra dimensions of string theory, each potentially giving rise to a different kind of universe with different laws of physics. Each of these universes might have its own holographic description. This connects to the multiverse hypothesis, the idea that our universe is just one bubble in an infinite foam of universes. If the multiverse exists, and if each universe is holographic, then the total reality is a vast collection of holographic projections, each encoding a complete universe on its boundary. and the boundaries themselves might be interconnected in ways we cannot yet imagine. This is extremely speculative, far beyond what current physics can confirm, but it shows how the holographic principle opens up new ways of thinking about the biggest questions in cosmology. Let me also address the question of consciousness more deeply, because it is something many people wonder about in the context of holographic reality. We have conscious experiences. We feel sensations, have emotions, think thoughts. How does this fit into a holographic universe? The honest answer is that we do not know. Consciousness remains one of the deepest mysteries in science and philosophy. We do not understand how physical processes in the brain give rise to subjective experience, and this hard problem of consciousness is not solved by the holographic principle. However, holography does provide some interesting perspectives. If information is fundamental, and if consciousness is somehow related to information processing, then consciousness might be more deeply woven into the fabric of reality than we assumed. The patterns of information that constitute your mind are part of the same holographic encoding that constitutes space-time itself. In this sense, consciousness is not something that happens inside the universe. It is an aspect of the universe, a way that the cosmic information processes and experiences itself. Some philosophers and scientists have proposed that consciousness might be a fundamental feature of information. In this view, called panpsychism or integrated information theory, wherever there is integrated information processing, there is some form of experience. Simpler systems have simpler forms of experience, and complex systems like human brains have rich conscious experience. If this is true, and if the universe is fundamentally informational, as the holographic principle suggests, then consciousness might pervade the cosmos. The universe might not be just a vast machine blindly following physical laws, but a vast mind, experiencing itself from countless perspectives. We, with our human consciousness, might be just one among countless ways the cosmic information comes to know itself. This is poetic and speculative, but it captures something that many people intuit when they contemplate the holographic universe. If reality is information, and if consciousness arises from information, then consciousness and reality are intimately intertwined. We are not strangers in a strange universe, so we are the universe awakening to itself. Let us also consider what the holographic universe means for the future of physics and the future of humanity. If the holographic principle is correct, it represents a paradigm shift as profound as any in the history of science. Our understanding of space, time, and reality would be fundamentally transformed. This shift is still in progress. The holographic principle is not yet a complete theory. We have the beautiful example of ADS/CFT, but we do not yet have a full holographic description of our own universe. Physicists are working hard on this, and there may be major breakthroughs in the coming decades. Or it may take centuries to fully understand how holography applies to cosmology. Regardless, the holographic perspective has already changed how physicists think about fundamental questions. It has provided new tools for calculation and new insights into quantum gravity. It has revealed unexpected connections between gravity, quantum mechanics, information theory, and even condensed matter physics. These connections continue to bear fruit. For humanity more broadly, the holographic universe is a reminder of how much we have yet to discover. Every major scientific revolution has revealed that the universe is stranger and more wonderful than we imagined. The Copernican revolution showed us that Earth is not the center of the cosmos. Darwin showed us that we are part of the web of life, not separate from it. Einstein showed us that space and time are relative, not absolute. Quantum mechanics showed us that reality at the smaller scales is probabilistic and entangled. The holographic revolution, if that is what we are witnessing, shows us that space itself may not be fundamental, that 3 dimensions may be a projection from 2, that information may underlie everything we see. Each revelation diminishes our parochial pride but expands our cosmic imagination. We are smaller than we thought, but the universe is more amazing than we dreamed. As we approach the end of this journey, I want to reflect on what we have learned and what it means for how we live our lives. The universe may be a hologram. This strange idea emerged from trying to solve a puzzle about black holes and has grown into one of the deepest insights in theoretical physics. The mathematics works. The pieces fit together. The evidence, while not conclusive, points in this direction. If true, the reality we experience is a projection, The three-dimensional world of objects and spaces is not fundamental, but emergent. Beneath our everyday reality lies a level of quantum information, of entanglement and encoding that gives rise to everything we see. This might sound nihilistic, as if the universe is somehow fake or meaningless, but I see it differently. The holographic universe is more tightly interwoven than we knew. Every part contains information about the whole. We are not isolated fragments, but expressions of a unified cosmic pattern. The information that makes up your mind is entangled with information across the universe. In a deep sense, you are connected to everything. The holographic universe also reminds us of the power of human inquiry. We are tiny creatures on a small planet, our lives lasting barely a cosmic eye blink. Yet we have managed to glimpse something profound about the nature of existence. Through mathematics and observation, through theory and experiment, we have begun to understand the deep structure of reality. This is remarkable. This is beautiful. This is what makes being human worthwhile, and we are far from finished. The holographic principle is not the final answer. It is a doorway to deeper questions. Why does holographic encoding happen? What determines the boundary? Is there something even more fundamental than quantum information? These questions await future generations of scientists and thinkers. So let this video be an invitation to wonder, to question, to explore. The universe has given you a mind capable of contemplating its own nature. Use that gift. Read about physics and cosmology. Ask hard questions. Never stop being curious. The hologram of reality is vast and beautiful, and we have only begun to explore its depths. What other wonders await discovery? What other assumptions about reality will future generations overturn? We cannot know, but we can be sure that the universe will continue to surprise us. I hope this journey has expanded your understanding and sparked your curiosity. The universe is stranger than we can imagine, and that strangeness is a source of endless wonder. If you have made it this far, thank you for your attention and your willingness to grapple with difficult ideas. This is what intellectual exploration looks like, following the evidence wherever it leads, even when it leads to places that overturn our deepest assumptions. Please leave a comment sharing your thoughts. Do you find the holographic universe compelling, disturbing, exciting? I want to know what you think, and if you found this valuable, please like and share so others can join this exploration. The universe is calling us to understand it better. Let us answer that call together. Remember, the next time you look at your hand or the stars overhead, you might be looking at a holographic projection from a distant boundary, a cosmic image encoded in patterns of quantum information. Reality is not what it seems, and that is the most wonderful discovery of all. Let me leave you with one final perspective. Throughout this video, we have been asking whether the universe is a hologram. But perhaps there is a deeper question lurking beneath. Not whether the universe is a hologram, but what it means for something to be real in the first place. We assume that real means three-dimensional material located in space and time, but the holographic principle challenges this assumption. If a two-dimensional encoding and a three-dimensional projection are mathematically equivalent, which one is more real? The question starts to seem confused. Maybe reality is not about any particular description, but about the underlying structure that all valid descriptions share. Maybe the deepest truth about the universe is not about dimensions or matter or even information, but about the patterns and relationships that remain invariant across all our ways of describing things. This is a more abstract notion of reality, but it might be closer to the truth. The universe is not any particular representation of itself. The universe is the thing that all valid representations represent. Thus, it transcends any single description, including holographic ones. If this is right, then asking whether the universe is really a hologram is like asking whether a cube is really a set of Cartesian coordinates or a set of spherical coordinates. The cube is neither. The cube is the cube, and the coordinate systems are just tools we use to describe it. Similarly, the universe is the universe, and holographic and non-holographic descriptions are just different tools for grasping its nature. This does not diminish the importance of the holographic principle, far from it. The discovery that the universe admits a holographic description is profound precisely because it reveals something about the underlying structure that we did not previously know. It tells us that the deep nature of reality allows dimensional reduction. That information is organized in particular ways, that space-time emerges from more fundamental structures. These are genuine discoveries about the universe itself, not just about our representations. So the holographic principle has taught us something real about reality, even if what it has taught us is more subtle than the universe is a hologram. It has taught us that our intuitions about space and dimension are not reliable guides to fundamental truth. It has taught us that information plays a more central role than we imagined. It has taught us that the questions themselves need to be refined as our understanding deepens. This is how science progresses. We ask questions, get partial answers, and use those answers to ask better questions. The holographic principle emerged from questions about black holes and information. It has led to new questions about the nature of space-time and the foundations of physics. Future discoveries will lead to questions we cannot yet imagine. The journey of understanding is endless, and that is part of its beauty. We will never reach a final answer, a theory of everything that explains every detail. But we will keep learning, keep discovering, keep being astonished by the universe's depth and strangeness. And so, as we conclude this exploration, I invite you to carry this sense of wonder into your daily life. The world around you, the ordinary world of objects and spaces, is the surface of an unfathomable mystery. Beneath the everyday lies quantum entanglement and holographic encoding and the emergence of space from information. You're walking through a cosmic hologram, and you are part of that hologram. And the hologram is thinking about itself through you. That is extraordinary. That is beautiful. That is the privilege of being a conscious being in this strange universe. Thank you for joining me on this journey. Until next time, keep exploring the mysteries of existence. The universe is waiting to reveal its secrets to those who dare to ask. The deeper we look into the nature of reality, the more we find that appearances deceive us. The solid ground beneath your feet is mostly empty space, with atoms held together by electromagnetic forces. The flow of time that seems so natural is actually relative, depending on your motion and the gravitational fields you pass through. The separate objects that populate your world are actually quantum entangled. Their fates interconnected in ways that transcend ordinary space and time. And now, perhaps most amazingly of all, the three-dimensional space through which you move may be a holographic projection from a two-dimensional surface. The depth you perceive, the distance between here and there, may be encoded in patterns on a flat cosmic screen. This is not mysticism or speculation. This is where the mathematics of physics has led us. It is strange and counterintuitive, but that is what we should expect. The universe does not owe us intuitive explanations. It is what it is, and our job is to understand it on its own terms. The holographic principle stands as one of the great intellectual achievements of our species. Emerging from questions about black holes and information, refined through decades of mathematical work, it now provides our deepest insights into the nature of space, time, and existence. It may be incomplete. It may be modified by future discoveries, but it has revealed truths that will endure. We are patterns of information, expressed in a holographic cosmos, capable of contemplating our own nature and the nature of reality. This is the human situation, strange and wondrous beyond measure. Let that wonder stay with you. Let it illuminate your days and nights. The universe is a hologram, and you are part of it, and it is magnificent. As we come to the conclusion of this extraordinary journey through the holographic universe, I want to bring everything together in a way that helps you understand not just what we have learned, but why it matters so deeply. We began with a simple question that sounds like science fiction. What if everything you see around you is not real? What if the three-dimensional world you inhabit is actually a projection? Like a cosmic movie from a distant two-dimensional surface. This question seems absurd at first. It seems to deny the obvious reality of the world we experience every day. But as we have seen, some of the greatest physicists of our time take this question very seriously. They take it seriously because the mathematics forces them to. The journey to the holographic principle began with black holes, those cosmic enigmas where gravity is so strong that nothing can escape. When Stephen Hawking discovered that black holes emit radiation and slowly evaporate, he inadvertently created a paradox that would reshape our understanding of reality. The information paradox asked a simple question. Where does the information go when a black hole evaporates? This question seems technical, but its implications are profound. If information is truly destroyed in black holes, then the fundamental laws of quantum mechanics are wrong. If information is preserved, then our understanding of black holes must be incomplete. For 30 years, the greatest minds in physics battled over this question. Stephen Hawking believed information was destroyed. Leonard Susskind and Gerard 't Hooft believed it must be preserved. The resolution, when it finally came, was stranger than anyone had imagined. The information was never inside the black hole in the traditional sense. It was encoded on the event horizon, the two-dimensional surface surrounding the black hole. Like a hologram, all the three-dimensional information that seemed to fall into the black hole was actually spread across its two-dimensional boundary. This insight led to the holographic principle, the idea that all the information in any three-dimensional region of space can be completely described by information on its two-dimensional boundary. The universe itself might be a holographic projection, with all of reality encoded on a distant surface at the edge of the observable cosmos. Juan Maldacena's discovery of the ADS/CFT correspondence turned this wild idea into rigorous mathematics. He proved that a five-dimensional universe with gravity is exactly equivalent to a four-dimensional boundary without gravity. The two descriptions are not just similar, they're identical. Every calculation gives the same answer in both frameworks. This was the holographic principle made precise, a mathematical demonstration that holographic universes are possible and internally consistent. Further research revealed even stranger truths. The very fabric of space-time might emerge from quantum entanglement. The smooth three-dimensional space we inhabit is not fundamental, but woven from the threads of quantum correlations. Space itself is a kind of quantum error correction code, a way of organizing information that creates the illusion of dimension and distance. The evidence for all this is growing. Studies of the cosmic microwave background have found patterns consistent with holographic models. The mathematics of string theory naturally incorporates holographic principles. The black hole entropy calculations match exactly what the holographic principle predicts. While we do not yet have definitive proof that our universe is holographic, the theoretical foundations are solid and the observational hints are intriguing. What does all this mean for you? What does it mean to live in a holographic universe? First, it means that reality is far stranger than our everyday intuition suggests. The three-dimensional world we see is a projection, an emergent phenomenon arising from more fundamental structures. The distances we perceive, the spaces we move through, are not fundamental features of existence, but consequences of how information is organized on cosmic boundaries. Second, it means that everything is connected in ways we did not previously understand. In a holographic universe, information is distributed non-locally. Every part contains information about the whole. The boundaries of existence are intertwined with the interior. We are not isolated fragments, but expressions of a unified cosmic pattern. Third, it means that information is more fundamental than matter, energy, or space-time. At the deepest level, the universe may be made of bits, not atoms. The physical world we experience emerges from informational structures. This connects to ancient intuitions, found in many philosophical and spiritual traditions, that the material world is somehow secondary to something more fundamental. Fourth, it means that our current understanding is incomplete. The holographic principle is not the final answer. It is a doorway to deeper questions. Why does the universe admit a holographic description? What determines the structure of the boundary? Is there something even more fundamental than quantum information? These questions await future exploration. And finally, it means that you, as a conscious being contemplating these ideas, are participating in something extraordinary. The universe has evolved creatures capable of understanding their own holographic nature. Through mathematics and observation, through theory and experiment, we have begun to glimpse the deep structure of existence. This is the great adventure of human inquiry, and you are part of it. I want you to carry this sense of wonder with you as you leave this video. The world you see around you is the surface of an unfathomable mystery. The ordinary is extraordinary when you understand what lies beneath. Every object you see, every space you move through, every moment you experience is part of a cosmic hologram, a projection from the edge of existence, encoded in quantum information stretching back to the beginning of time. You are part of this hologram. The information that constitutes your body and mind is entangled with information across the cosmos. In a deep sense, you are connected to everything that exists. The holographic universe is not something separate from you. It is what you are. This perspective does not diminish the value of your life. If anything, it enhances it. You're not just a random collection of atoms on an insignificant planet. You are an expression of the fundamental informational structure of reality. You are the universe experiencing itself, contemplating its own nature, asking questions about its own existence. And so, as we conclude this exploration, I leave you with gratitude and wonder. Thank you for taking this journey with me. Thank you for your curiosity and your willingness to grapple with difficult ideas. Thank you for being part of the great human quest to understand the cosmos. The universe is calling us to understand it better. The holographic principle is one response to that call, revealing that reality is stranger and more beautiful than we ever imagined. But there is so much more to discover. Future generations will build on what we have learned and will uncover truths that will transform our understanding yet again. Keep asking questions, keep wondering, keep looking up at the stars and asking what lies beyond. The hologram of existence stretches out before us, vast and mysterious and beautiful. Let us explore it together. I hope this video has changed how you see the world. I hope it has sparked your curiosity and filled you with wonder. The universe is an amazing place, and we are privileged to be conscious beings capable of contemplating its nature. Please like this video if you found it valuable. Share it with friends who love to think about the big questions. Subscribe to this channel for more explorations of the deepest mysteries of space, time, and existence. And leave a comment telling me what you think. Do you believe the universe is a hologram? Has this video changed your perspective? I want to hear from you. Until next time, remember, the world you see is not what it seems. Reality is a hologram and you are part of it, and that is the most wonderful thing of all. Keep exploring, keep questioning, keep wondering. The universe is waiting to reveal its secrets, and you are the universe, wondering about itself. End.